Hello, today we're going to talk about impulse and momentum. We're going to start out with the situation of a person kicking a soccer ball. And we can see that the ball begins to be compressed as the contact between the foot starts, but it takes time to compress the ball. So the foot and ball are in contact with each other over a time period. And during that time, the foot is applying a force to the ball. Um, and here is a graph of force over time. So we have at the beginning, um, the contact first begins, there's only a bit of the maximum force that is applied to the ball at the beginning. Then we get to a point where the maximum force is applied. This is also the point of maximum compression of the ball. And then the force starts to drop off as the ball starts to leave the foot. And all collisions work like this, but the duration, of the collision depends on the material. So harder objects like pool balls, for example, have a shorter duration than the soccer ball in the foot, because you can see here that both the soccer ball and the foot compress slightly during this collision. Whereas if you can think of two pool balls or billiard balls, when they collide, even in like the same kind of snapshot frame of photos, we would not see anything like this compression that we see. So that tells us that their collision happens much faster. And we can find another thing, or we can take another thing from a graph of the force of versus time during a collision. The area under that graph is known as the impulse, and that's the average force times the time interval. This is the impulse due to a force acting for a duration of time. I want to talk about why it is the average force. So realistic force curves are going to be gradual, both in the initial buildup of the force to the maximum point and then the decrease also. But it's kind of hard to work with that sometimes. So another way to look at it is we can take the average force instead, and that way, as soon as the collision starts, we can just assume that this whole area is the average force. And the area here and here is actually the same. So it works out just fine. And it's the same duration of time also. So now tied with impulse is the concept of momentum. First, I just want you to look at the image. We have a hockey puck, and it's going with an initial velocity, and then it is hit with a stick and experiences a force for a certain amount of time, and then it has a bigger velocity. So I'm first just going to tell you that impulse, which is given by a capital J, by the way, is the change in momentum. And momentum is given by the mass times the velocity, but we're going to derive this. Okay, so to start out, we have the impulse equation where it's the average force times the time interval. And I'm also going to treat the average force as mass times the average velocity. And one additional point here, mass times the average acceleration, not average velocity. The equation for average acceleration is just the equation we kind of initially learned for acceleration. So v final minus v initial over the time interval. Okay, so now we want to solve this equation for the average acceleration. So average acceleration is just the average force over the time interval, or I'm sorry, over the mass, mixing up the part, over the mass. And it also is equal to this over here, so we can set those equal to each other. So we have the average force over the mass is equal to the final velocity minus the initial velocity over the time interval. And now if we do a little rearranging, and I will walk you through the rearranging each step. So first we're going to multiply both sides by the time interval. And actually in this step, we will also multiply both sides by the mass. So we now end up with the average force times the time interval equal to the mass times the final velocity minus the initial velocity. But we just learned that the average force times the time interval, that's just the impulse. And this, as I said, I know I gave it away at first, but this is actually the change in momentum. So this is, if we distribute the mass there, we have mv final minus m the initial. And when we have something that is final minus initial, that's change in. So what we end up with is change in momentum is equal to the impulse. So it just comes from the relationship between impulse and force, really. And then from force, we connect in acceleration, which brings us velocity. So anyway, this is where this relationship comes from. This is another one of the things, those things where you don't need to be able to derive it. I just don't want you to, like, I don't want to give you a mystery equation. Okay, back to the slide. So again, we just saw how this is true, that the impulse is equal to this change in momentum, and this is where a change in momentum comes from, but it's also something reflected in the real world. When an object has an initial velocity and then a force is applied to it over a certain amount of time, it has a change in that velocity. So another thing about both momentum and impulse is that they are vectors. So we have to remember what we know about vectors. And so momentum is mass times velocity. Mass is not a vector, but velocity is. So momentum and velocity point in the same direction. And the change in impulse, the change in momentum, which is the impulse, is also a vector. So for example, if you have the initial and final momentum, you can get the change in momentum, which is the impulse. And by that, I mean the vector form of these things. So this relationship between impulse and momentum gives us the impulse momentum theorem. So, and that just says an impulse delivered to an object causes the object's momentum to change. So that is what we have seen. An impulse, which again is the average force times the time interval, is the change in momentum, which is final minus initial. Here's just a couple examples of other collisions and how this plays out. So for the top one, we have a golf club hitting a golf ball. And golf ball is a lot harder than a soccer ball, for example. So we do see, I mean, this is a graphic, but still, we see a slight compression of the ball during the collision. And so it started with no momentum because it wasn't moving. And then it was hit with the club and it experienced an impulse, and then it has a final. And so with this one, because the initial momentum was 0, we just end up seeing that the final momentum and impulse are the same. But let's say in this other example, we have a soccer player. And this soccer ball initially had a momentum. It had velocity toward the player's head. And then their head delivers an impulse to the ball, which changes the momentum. So this one is a more, it's not as simple. situation. So this time we have to find the change in momentum, which is the impulse. And you can see that this version of the vector diagram is not what we usually use, but you could rearrange it to be P final minus P initial, and get the impulse also. We can draw that, not right now. So now I have a question I want you to try and do on your own, but let me read it to you. A puck seen from above was moving with an initial momentum when it received an impulse from a hockey stick. Which arrow best represents the puck's initial momentum? So initially the puck is moving in some direction, then it receives this impulse to the right, and then its final momentum is pointing up and to the right. So we want to figure out what the initial momentum was. And with this, I'll just point out that you can rearrange the equation. So impulse equals the change in momentum, which is final minus initial. But we want to solve for initial here. So we can rearrange that equation and still do the same kind of vector addition or subtraction, we've done before. I'm going to pause a second in case you want to pause this and try and work it out. And then we will take a look. So this again is not the form of the vectors that we, of vector addition that we've been using. But you can see that in order for the final momentum to point up and to the right, the initial momentum needs to, at the very least, point up. And then our only option for pointing up is D. So our initial momentum is pointing up and to the left. So D is the answer here. And if this is a little bit unclear, I highly recommend drawing the vector map yourself. Now I want to talk to you a little bit about collisions, but also cars and the water barrels, those big yellow barrels off the side of the highway. So we are going to talk about that a little bit. Okay, so how this is going to go, first we're just going to talk about this situation, and then I have an example to show you. So just in general, think about a car coming to a stop, which means the final velocity is 0. And you can kind of think about what that means for both the passengers and the car itself. So, weird, there we go. The initial momentum is not 0 because it started with some velocity, but the final is. And we know that the impulse is the change in momentum. Give those both a vector. And we also know that this is the average force times the time interval. So let's put that here. We have the impulse is the average force times the time interval, which is the change in momentum. And in this case, our initial momentum is 0. So change in momentum is the final minus the initial, but the initial, the final is 0. So we just end up with negative P initial here, negative initial momentum. So let's take a look at this part and that part of the equation. So we have our average force. I'm going to drop the vector label for now. And this is equal to negative initial momentum. And then we could get the force by itself by just not the right math, dividing the time interval on both sides. So from this, we see that the average force needed, and remember, this is a car coming to a stop. So we're talking about the force needed to stop the car from whatever its initial momentum is the initial momentum divided by the time interval. But what that tells us is actually that the average force needed to stop anything, but also specifically a car, is proportional. This is proportional. Proportional to 1 over the time interval. And what that really means is the bigger the time interval, smaller force is necessary. But the opposite of that is also true. The smaller the time interval, a bigger force is needed to bring the object to a stop. So, and now I will show you with the example how this connects to the water barrels on the highway and cars and things. So let me read you the problem. As part of a safety investigation, two 1,500-kilogram cars traveling at 22 meters per second are crashed into different barriers. And we have two questions. What is the average force? Sorry, I think I have a typo in that sentence, but if it hits water barrels and stops in 1.3 seconds, or if the car hits a solid barrier and stops in 0.18 seconds. So let's take a look. Let's write first, I think, our knowns like we have done all quarter. So the mass, 1,500 kilograms. Our initial velocities for both of them are 22 meters per second. And our final is 0. And then the next part, I'll break that up between the two parts. So for A, the time interval is 1.3 seconds. And now, so we're looking for the average force, and we just solved and saw that the average force is the negative initial momentum divided by the time interval. So we're going to use that. We're not going to rederive it. Negative initial momentum divided by the time interval. So momentum is mass times velocity. So we have negative 1,500 kilograms times 22 meters per second divided by 1.3 seconds. This gives us an average force of 25,400 newtons, which is big. And this is negative. That's really just telling us the direction. It's not a big deal for understanding this example. Okay, so that's a pretty big force, but let's see what happens if you have to stop in much less than a second. So if instead our time interval is 0.18 seconds, go back to our equation, we'll just write it again. So P, okay, negative 1,500 kilograms times 22 meters per second divided by 0.18 seconds. So this gives us an average force of 18 times 10 to the 4 newtons. So this one, let's see, this is like 2.5 times 10 to the 4. So this is a lot bigger of a force. So that is why a couple of things with cars. That is why they have those water barrels on the highway so that you can bring your car to a stop over a time frame so that less force is necessary to bring it to a stop because you're in it. So you'll feel that. That's also why cars have crumple zones. That is why like the hood of the car will kind of crumple up. It is to increase the time it takes for the car to come to a stop. And I will also say this is why it is not a good idea to ride in a Cybertruck because they do not crumple. And you know, that means big force and you're in the car, you're the one who experiences the force. So anyway, just be careful with that. Okay, back to the slide. Just kidding, not back to the slides. I have another example. This one is not related to cars or crumple zones or anything like that. It's just a regular collision. We have a ball of mass 0.25 kilograms rolling to the right at 1.3 meters per second, and it strikes a wall and rebounds to the left at 1.1 meters per second. What is the change of the ball's momentum, and what is the impulse delivered to it by the wall? So let's write down our information. Our mass is 0.25 kilograms. Our initial velocity, and this is the point where we need to be careful. We need to pay attention to the direction of motion here. So we are going to stick with our convention that the positive axis to the right, or positive motion is to the right. So that way, after the collision, when it's moving to the left, it's negative. So we have an initial of 1.3 meters per second, and then our final, oops, that's just initial again. Final is negative 1.1 meters per second. Then let's write some of the equations we know. So change in momentum, which is what we're looking for, is the final minus the initial. And momentum is the mass times the velocity. So we can just plug in our numbers and solve this. Not bad, pretty straightforward. 0.25 kilograms times the 1.3 meters per second minus, yes, still minus 0.25 kilograms times negative 1.1 meters per second. And what this gives us is an impulse. Oh, oops. My bad. I messed up here. I switched around final and initial. Let's try that again. Sorry, I wrote it up there and I didn't even do it right. Okay, so the final velocity is the negative 1.1. So let's try this again. 0.25 kilograms, negative 1.1 meters per second. Okay, and then we subtract the initial, which again, 0.25 kilograms, and this one is positive 1.3 meters per second. Okay, now that we corrected that, what we get is negative 0.6 kilogram meters per second, which I haven't explicitly said this, but that's the units of momentum. They don't get their own units. It's just what makes up momentum, which is mass and velocity, kilogram meters per second. So that is the change in momentum. And also know that the change in momentum is equal to the impulse. So that's also the impulse. Negative 0.6 kilogram meters per second. So this question had two parts, but we only have to do one. Okay, now we're actually going back to the slide. Okay, so now I just want to kind of introduce a couple of things. So one idea is the total momentum. So here we have three different billiard balls or pool balls. And each of them has their own momentum because they're rolling in different directions. But if we take them as a system, we can sum up their momentum and get the total momentum for the system. And again, this is vectors. We've dealt with vectors. So to get the total momentum, you just do vector addition with all of the different momentums. And then I want to talk more about collisions. So I mentioned collisions with since the start of this lecture, but most of the time, we were really just looking at one piece of it. So that last example, it was the ball we were looking at, but it did collide with the wall. So another thing we can do is look at collisions between two objects. And one important point is, so these objects collide with each other. They both experience an average force from the impulse of their collision, and that's an action-reaction pair of forces. So they experience equal magnitudes of force, but in opposite directions. And since the impulse's force, our average force, times the time interval is going to be the same. They're colliding, so they're both experiencing it for the same amount of time. And since the force is also the same, just different direction, their impulse is the same. So the impulse of object one is equal, well, sorry, equal and opposite in direction. So the impulse of object one is equal to negative the impulse of object two. And the impulse is the change in momentum. So what we also find is that the change in momentum of object one is negative the change in momentum of object two. But again, I also just defined the total momentum as the sum of the momentums of the objects in the system. So what that tells us is that if we take two objects that are going to experience a collision and treat them as a system, we can say that the initial momentum of that system is equal to the final momentum of that system. So that's telling us that in a collision, the total momentum is unchanged by the collision. So a little bit more on systems. In forces internal to the system don't change the momentum, which is actually what we just saw with that example of if we treat those two objects as being in a system, then the collision doesn't change the total momentum of the system. So the same is true for a bigger system, or at least when you like intentionally label it as such. External forces, as in forces coming from or going toward objects not within the system, those do change the momentum of the system. And so, though, the momentum of an isolated system, as in one that doesn't experience external forces like these, that a momentum of an isolated system is conserved. And this works just like conservation of energy. When there isn't external work done, which is external forces, just like in this example, then the energy of the system is conserved. So here, if there are no external forces, then the momentum, the total momentum of the system is conserved. And on Tuesday, we will use this idea to solve the more complicated collision. That is all I have for you. Thank you.